Okay, so here we are. We're going to talk about the sampling distribution today, and very exciting. This is one of our last units of the year. So I'm going to record all the notes for all the people that are not here today. So first, let's just go through some vocab. So a parameter, we've talked about parameter and statistics before, but I wanted to throw them on the vocab sheet because they become very, very important in the next couple days' discussions. So a parameter is a number that describes a population. So that would be maybe the mean of a population, or a standard deviation for a population, or a proportion. So let me just write down some of the symbols that I'll use for parameters. Things like mu for the mean of a population, sigma for the standard deviation, p for a particular proportion for a population. So it's a lot of times you'll see a Greek letter. And it's just a number that describes an entire population. Versus a statistic, which is a number that describes a sample. So that's, I just take a small collection from the population, and then the numbers that come from that small sample, they're called statistics. So I might have like a mean, which I'll denote maybe with x bar, or a proportion, which I'll denote p hat, or maybe the sample standard deviation, which I'll call s. So the key idea for today is that parameters and statistics they're both numbers. It's just parameters describe the whole population. Statistics come just from samples. So obviously what we're going to look at today is that we want to know oftentimes what the parameter is for a population, but the population might be so large that we can't go out and look at every data point in the entire population, like sample everybody. So we'll just take a small random sample and get some statistics from our samples, and then we obviously want the statistics to be unbiased estimates of those parameters. That's kind of the goal. So let's just look at a couple of examples here. So we want to identify for the numbers in these given scenarios, are they a parameter or is the number a statistic? So in this first one, the Bureau of Labor Statistics last month interviewed 60,000 members of the U.S. labor force, 7.2% of whom were unemployed. So we've got to think for a second, this 60,000 people, is this every single member of the U.S. labor force? Now we definitely say no, because there's the total population of the country is probably over 300 million. And there's millions and millions of people that are in the labor force. So this 60,000 members is a sample. So the percentage that's coming from this sample of how many people are unemployed, that's a statistic. So 7.2% of those people are unemployed. That 7.2% is a number that describes the sample. So that's a proportion coming from a sample. So in this case, I would call that p hat. P with a little caret over it. That equals 7.22%. That's a statistic. That's a stat. So number two, we've got this telemarketing firm in LA. They use a device that dials residential telephone numbers in that city at random. Of the first 100 numbers dialed, 48% are unlisted. This is not surprising because 52% of all LA residential phone numbers are unlisted. So of this first 100 numbers dialed, that's a random sample of 100 phone numbers, and 48% are unlisted, so that is a statistic, that 48%. Let's say p hat is 0.48. That is a stat. It's a statistic. So the other number in this problem, this 52%, that's a parameter because that number is describing all the people in LA. So that's a parameter. So I would denote that as p equals 0.52. So notice I'm using different symbols to differentiate between statistics and parameters. So notice I said that p hat was equal to 0.48. That lets me know that that 0.48, that 48%, is a number describing a sample versus the 52%, I called that, I said p equals 0.52 to let me know that 52%, that's a number that describes an entire population. It's not just coming from a sample. Okay, what do we got, number 3? A truckload of cylinders has a mean diameter of 2.5003 centimeters. So that number, that's the average for all of the cylinders in the truck. And then it's saying a random sample of 100 cylinders from the truck has a mean of 2.5009 centimeters. So the 2.5003, that's all of the cylinders in the truck, so that's a parameter. That's the mean for all of the cylinders that's in the truck. So the 2.5003 centimeters, that's the mean of all the cylinders. The mean of the random sample of 100 cylinders, that's a statistic. So the x bar equals 2.5009 centimeters. That's a statistic because that's just the mean of the random sample of 100 cylinders. So for all these problems that we're going to do, it's important that we differentiate between the numbers that describe a sample versus the numbers that describe an entire population. Okay, so let me move this down here. So now we're going to talk about this notion of a sampling distribution, which is all possible samples of a certain size. So let me write that down. So that's the distribution of all possible statistics from samples of a given size. I usually call n my sample size. Okay, so I made a mistake that I'll correct here. This should be the distribution of all possible samples. Made a correct that typo. Okay, so now let's talk about bias and variability. I mean, we've been talking about variability a lot this year. Variability is just a fancy word for spread. So when you're talking about how variable something is, you're talking about how spread out something is. And we know numbers that describe the spread. We can use things like the range and the interquartile range and the standard deviation, all measure how spread out the data is. So when you're talking about how variable the data is, how variable various statistics are, you're talking about spread. And then bias is how well the stats reflect what the parameter actually is. So if something is unbiased, if a statistic is unbiased, that means it's close to the parameter. If a statistic is biased, that means it's far off the parameter. So bias reflects how close a stat is to the parameter. So we can think of a lot of these in terms of pictures. So I'm going to actually draw D first. So what would it look like if I took some results and it was low bias and low variability? Well, that would be something like this. That would be like there exists some number, say, for Framingham High School. Say, like we were just talking about the proportion, like how many guys go here versus how many girls. So there exists some percentage of the number of guys that go here. We'll call that P, the percentage of guys that go to Framingham High School. Or the percentage of all kids that are at Framingham High School that are guys. Okay, so if we went out and we got a bunch of random samples and the samples had low bias, that means that the percentage of guys in our samples was really close to the percentage of guys that go to the school. So if I made a histogram of those percentages, they'd be like really close to P. And low variability means that the results are not really spread out that much. So low bias means that the statistics are going to be close to the parameter, and low variability means there's not a lot of spread. So let's contrast this with low bias, high variability. Okay, low bias means the results are still pretty accurate, but they're going to be more spread out. So maybe something like this. There's my histogram. So notice the center of the histogram is still centered at P, but notice that the histogram is way more spread out than the one that I drew in part D. So it's highly variable. There's a lot of spread in the histogram. The histogram is still centered on the parameter that you're measuring. Okay, so now A and B are talking about, well, what if the bias was high? Well, that would be something like, let's look at this. So here's P. So if the bias was high, that means that the measurements that I'm getting, the statistics that I'm getting from my samples, are not close to the parameter that I'm measuring. So that means my histogram might look something like this. So notice there's not a lot of spread there. Like all the results are clustered really close together, but notice how the center of the histogram is way off of the parameter that I'm trying to measure. So it's not a lot of spread, but it's missing the mark. That's what high bias means. The sample statistics are really far off of the parameter. And then this last one, C is probably the worst case scenario. This is what you just definitely don't want to see. It's like where your statistics are missing the mark, they're not good estimates, and they're wildly variable, so they're all over the place. So you might see something like this. Get a histogram like this. So it's wildly variable results, and the results are nowhere close to the number that I'm actually trying to measure. So C is kind of like the worst case scenario. That's what I just never want to see when I do an experiment or when I do an observational study. Okay, we're back on the second page here. So now we're just going to kind of mathematize this. We're going to, put some math behind these ideas, talking about how this applies to the idea of the normal distribution, which we just kind of were introduced to in our last unit. So, okay, so we've got these ideas of the population proportion, the sample proportion, mean, z-score, standard deviation. So for the population proportion, I'm going to use the letter P, and for the sample proportion, I'm going to use P hat. P with the triangle over it. So the mean of a particular population is going to be the population proportion. So when I'm talking about proportions, the mean of all the proportions, that is P. So the mean of all of the P hats in existence does equal just P. And we've got kind of a formula to compute the standard deviation. That's P times 1 minus P over the sample size and the square root of all of that. And if we investigate the binomial distribution a little bit later on in the year, we can kind of see where that comes from. But for today, that's just kind of like a given. I'm just telling you the formula for today. So now we can compute z-scores when we're talking about proportions, and it's the same way that I would compute a z-score before. Like nothing changes here. Like before I was doing the value, the stat, minus the parameter divided by the standard deviation. So before it was x, which was like one value from the population, minus mu, which was the parameter, divided by the standard deviation. Same thing here, but now the statistic is p hat minus the parameter divided by the standard deviation. So it looks like it's a different formula, but it's really not. So when I say like x minus mu, that's one number, one value from the distribution minus the average divided by the standard deviation. I'm doing the same thing here. P hat is one sample proportion minus the parameter, which is p. So I'm just shuffling around letters, basically, but the math hasn't changed at all. It's always stat minus parameter divided by the standard deviation. Okay, so let's look at some examples, and we'll see that the math is kind of exactly what we were doing here. So we ask a simple random sample of 1,500 first-year college students whether they applied for admissions to any other college. There are over 1.7 million first-year college students in general. In fact, 35% of all first-year college students applied to a college other than the one they're attending. That is the proportion for the entire population. That is the parameter. Assume the distribution of sample proportions is approximately normal, and then we're going to compute these probabilities. So that 35%, that's the number that describes the sample. So that's P. The sample size is 1,500. So the first thing I'm going to do here is I'm going to compute the standard deviation using the formula from above. So it's P times 1 minus P, 1 minus 0.35 is 0.65, divided by the sample size, the square root of all of that. So that's going to be, let me grab my calculator, 0.35 times 0.65 divided by 1,500, get that answer, and then take the square root of that answer. I get that the standard deviation is about 1.23%. Great, so now I want to figure out some of these probabilities. So I want to figure out what are the chances that I take a sample and my sample has a greater, the sample proportion is greater than 37%. So I'm figuring out the probability that p hat is greater than or equal to 0.37. So now the math here is going to be sort of the same stuff that we did before. Figure out the z-score, draw a picture, and then you're going to use the calculator to get the probability. So I'm definitely going to run out of space here. So you know what I'm going to do? I'm going to grab my eraser. Since I have these numbers written down here, I'm going to erase because I'm going to need the space over here to do some scratch work. So on the side here, I'm going to draw my picture. So here's my normal curve. 0.35, the mean goes in the middle. 0.37 goes over here. I'm figuring out the probability that I would get a sample proportion greater than that. So there's my picture. So I need to find a z-score that corresponds to that 0.37. So it's going to be p hat minus p divided by the standard deviation, which is 0.0123. That z-score should be positive because the sample proportion is to the right of the mean. I get a z-score of 1.63. So now how am I going to figure out this area under the curve? I'm going to do a normal CDF of 1.63 to infinity. Normal CDF. And remember, when you're using the normal CDF function, it's the starting z-score and the stopping z-score. So the starting z-score is 1.63. but then I'm looking for that entire right tail probability. So it's the starting z-score is 1.63, but then the ending z-score is infinity, which I could just type in as a string of 9s. So I would do normal CDF, 1.63, comma 9999. I get 0.0516. So what this is saying is, if I took a random sample of 1,500 college students, there's about a 5% chance that in that sample, 37% of them or more applied to more than one first-year college. Applied to more than one college. So I don't really have enough room to write that sentence, but I said the sentence I would write on the test. So the key things here for stuff that you should write down is make sure you're writing down the probability statement, and make sure you're saying what the answer is, obviously. Make sure you've got that picture, make sure you showed the z-score and the work for that, and make sure you write a sentence, kind of summing everything up. You do not need to write the calculator, the normal CDF of 1.63 to infinity. You don't need to write the calculator notation on your test. So we're going to take a break here, try to figure out B and C, and then I'll come back with the answers in a second.
Calm down.
Okay, so we worked out a bunch of these problems in class, so you should have gotten, for this, I'm not doing all the work, I'm just writing out the answer, 0.007, and for part C, you should have gotten about 94%. Okay, so I want to go through this last example before the bell rings here. So the first thing I would do in this problem is I would write down what the proportion is for the population, which is that 15% of all the adults jog in the entire United States, or whatever this population is. So that's P. My sample size is going to be 1,540 adults. So I'm going to find the standard deviation, which is P, times 1 minus P, which is 0.85, but I'm just writing it out, over 1,540, and I just realized I got an extra 0 there. The square root of all that, that gives me 0.009, so a little bit less than 1%. So now, the question is asking me, I'm going to draw my picture here. So I know that 15% of all adults jog, but I'm looking for, if I took a random sample of adults, what are the chances that I get that more than 13.5% of the adults jog in my sample? So I'm looking for all of that area. Now, just by looking at the picture, I know that the answer has to be more than 50%. So I need to find a z-score. So it's P hat minus P divided by the standard deviation, and I get a z-score of I'm just doing the computation now. I get a z-score of negative 1.67. So now the answer, so the probability that P hat is greater than or equal to 0.135 is going to be the normal CDF of negative 1.67 out to infinity, which gives me about 95%, 95.2%. So there's about a 95% chance that if I took a random sample of 1,540 adults, that 13.5% of those sampled or more would say that they do jog.